Welcome back. In today's class, we will start with the last module, Module 5, and the Module 5 deals with the power absorbing devices or power absorbing turbo machines. In Module 1 and 2, we studied about the basics and general analysis of turbo machines, which included both power absorbing as well as power producing turbo machines. In Module 3, we studied about steam turbines, which is a power producing machine, and in Module 4 we studied about hydraulic turbines, again that is a power producing turbo machine. Now in the last module we will study about the power absorbing turbo machines. So in this module we will study the performance of centrifugal pumps, centrifugal blowers and axial flow centrifugal compressors. In today's class we will start with the centrifugal pumps. First, let us see the classification of centrifugal pumps. The centrifugal pumps are classified based on several parameters. The first one is based on the working head. So based on the head developed by the pump, here we are dealing with power absorbing turbo machine. So what it does is it converts the mechanical energy of the impeller or the runner into fluid energy. In the case of power producing turbo machine, the fluid energy will be converted into mechanical energy, and that can be coupled to a generator or a prime mover that can be coupled to a generator to produce electricity. But here what we are doing is we are converting the mechanical energy of the impeller or the runner into fluid power. We are going to store the water or the other fluids at a higher energy level, maybe at a higher position, at a higher height, or maybe in the form of compressed air. When we are dealing with power absorbing turbo machine, what we are doing is we are converting the mechanical energy of the impeller into kinetic energy or the fluid power. In most of the cases, the fluid power which we need will be in the form of increase in the pressure energy. In the case of centrifugal pump, what we do is we increase the kinetic energy of the fluid. The impeller will impart kinetic energy onto the fluid, and that will be converted into pressure energy with the help of the casing, and then that pressure energy is utilized to pump the liquid into a higher level, and there it will be stored. So that is the basic function of a centrifugal pump. So what we do in a centrifugal pump is that we increase the pressure energy of the fluid, and for that we provide mechanical energy as input for the impellers. So now let us see the classification of the centrifugal pump. So it is classified based on several parameters. The first one is based on the working head. Based on the working head, the centrifugal pump is classified into three categories. One is low head pump, the second one is medium head pump, and the third one is high head pump. In the case of low head pump, the head developed by the impeller or the head developed by the pump will be up to 15 meters. We will see what are these heads later, but in this case the pump is able to produce a total head of 15 meters. So these are called low head pumps. Generally they are small in size. Then we have the medium head pumps, where the pump can produce a head of up to 16 to 40 meters. So the total head developed by the pump will be in the range of 16 to 40 meters. Then we call those kind of pumps as medium head pump. Then we have high head pump, where the head developed by each pump will be more than 40 meters. And generally we go for the medium head pumps are used in industries, as well as in some of the cases maybe in apartments. High head pumps are generally used for industries. Then based on the number of impellers, we have a single stage pump, and then we have a multi-stage pump. Generally, the pumps which we use on our house to pump water from sump to the overhead tank, they are single stage pumps. So, we will have only one impeller on the shaft. So, the shaft is powered by a motor, and on that shaft there will be only one impeller. If you have multiple impellers, for example, there are two reasons to have multi-stage pumps. One is if you want to increase the head developed by a pump, then what we do is the output from the first stage of the pump will be input for the second stage of the pump. So thereby the head developed by the first and second stage will be added together, and we get a higher, we can deliver the liquid to a higher level than if you are using a single stage pump. Otherwise, in some cases we need to deliver a large quantity of water. We need a large discharge, and single pump is not able to achieve that discharge for the given head. In that case, what we do is, instead of using a single stage pump, we have multiple stage, maybe 2 or 3 stage of pump, where all the stages develop the same head, but they deliver equal quantity of water or liquid, thereby increasing the amount of liquid pumped through the pump. So that is where we go for multi-stage pump. Then based on flow direction, we have the radial flow pumps. If the flow is radially outward, then we call them as radial flow pumps. So if you have a shaft and the fluid is flowing perpendicular to the shaft, then we call them as radial flow pumps. Then we have axial flow pump. So generally we go for radial flow pump where the head developed should be higher, and we have axial flow pump where the flow will be parallel to the axis. So if this is the axis, then if the flow is parallel to the axis, then we call them as axial flow pump. And generally axial flow pumps are used when the head developed is less but the discharge is very high, because when the fluid is flowing in the axial direction, there will be very less restriction for the flow. The inlet and outlet will have a very large area, so it can accommodate a high discharge of the liquid. In the case of mixed flow pump, when you have a moderate height and a moderate amount of discharge, then we go for a mixed flow pump. So those are the mixed flow pumps where the fluid enters parallel to the shaft or in the axial direction and leaves the pump in radial direction. So these are used where you have medium head and medium amount of discharge needed. Then based on the fluid entrance, we have single entry pump. The household pumps will have only one entrance and one exit. So if you have only one entrance, then we call them as single entry pump. If you have multiple or two entry, then we call them as double entry pump. So in the case of double entry pump, there will be two inlet pipes through which, or the suction pipes through which the liquid will enter the casing of the, or the liquid will enter the casing of the pump. Then based on the type of casing, we have volute casing pump, then we have vortex casing pump, and we have diffusion pump. Based on liquid handled, we have closed impeller pumps. The pumps, the centrifugal pumps which we use on our day-to-day life to pump water from our sump to the overhead tank, they are closed impeller pumps. Closed impeller pumps are used when you are handling very low viscous fluid. So when you are handling low viscous fluid, it flows very easily. So you can have a closed impeller. Closed impeller pumps are used for liquids which have very low viscosity, for example water. Then we have semi-closed impeller pumps. If the viscosity is slightly higher, then we go for semi-closed impeller pump, where part of the impeller will be closed and at the inlet we will have a larger opening. So this helps to accommodate larger mass flow rate, and if the viscosity of the fluid is slightly thicker or more, then the fluid offers resistance. For that case, we provide semi-closed impeller pumps. Then we use open impeller pumps for handling very highly viscous fluid. So if the viscosity is very high, then it is difficult or it requires a lot of energy to move them. For that purpose, we go for open impeller pumps. Now let us come to the different parts of the centrifugal pump. The major parts are the impeller, casing, suction pipe and delivery pipe. So the impeller is the mechanical device which will be rotating inside the casing, and that will transfer its energy to the fluid. So the energy interaction happens between the fluid and the rotating impeller inside the casing in a centrifugal pump. So then we have the casing. Casing is necessary because, as I said, centrifugal pumps are reaction devices, reaction turbo machines, and for a reaction turbo machine we need to have a proper enclosure so that the energy transfer will be efficient and the impeller will be able to transfer a large amount of energy to the fluid. The impeller imparts energy to the fluid in the form of kinetic energy, and that kinetic energy will be converted into pressure energy with the help of the shape of the casing. So the casings will be designed in such a way that it converts the kinetic energy of the fluid into pressure energy. And then we have the suction pipe. So here we have the pump. You can see this is the suction pipe. The suction pipe has a foot valve at the bottom. Foot valve is a non-return valve which allows flow only in one direction. So from the sump towards the pump. So that is the suction pipe. Then we have the delivery pipe. Delivery pipe is the pipe that is connecting the pump, outlet of the pump, to the delivery tank. That is the delivery pipe. Now let us come to the terminology of centrifugal pump. So when we are designing a centrifugal pump, we will be coming across a lot of terminologies. First, let us look into this diagram. So here we have the delivery tank, we have the pump, this is the delivery pipe, this is the suction pipe, this is the suction side of the pump, and this is the delivery side of the pump. Then at the suction side of the pipe we have the foot valve. As I said, foot valve is a non-return valve. It allows the flow of fluid only in one direction. The casing provides an airtight seal for the impeller, and we need to ensure that there will be no flow of water from the suction side into the sump when the pump is not running. When the pump is not running, if there is no liquid in this pipe, in the suction pipe, then the impeller will be just rotating. It won't be able to pump water or suck water from the impeller, so from the sump. So to suck water or to draw water from the sump, this entire thing should be, the suction pipe should be filled with the same liquid. So here we are talking about the sump, or here we are talking about liquid water. So it is applicable for any other liquids. So for that reason we have a foot valve which will have a strainer. The strainer is provided to make sure that no solid particles will enter the suction pipe, and at the same time there will be a non-return valve, so that prevents the flow of water from the suction pipe into the sump when the pump is not running. Here we have the foot valve, then this is the sump level, and the height from the sump level to the center of the pump we call it as suction head, and from the center of the pump to the level of liquid in the delivery tank we call it as delivery head. The sum of suction head and delivery head we call it as static head, and then we have HM monometric head, and we have HFD plus VD square by 2. So VD is the velocity of the fluid when it comes out of the delivery pipe, or velocity of the liquid in the delivery pipe. So that is the loss which occurs because that is the amount of energy we will not be able to utilize, and since we are just dumping water into the delivery tank, so there we are losing that much amount of energy. And HFD is the frictional losses that occurs in the delivery pipe. When it comes to here, from the sump level to the footwall level, so we have HFS plus Vs square by 2. Vs square is the velocity of the water in the suction pipe, and HFS is the frictional losses that occurs in the suction pipe. So these are the different terms. So now suction head is the height difference between the sump level and the center of the pipe. Then we have the delivery head, which is the height difference between the center of the pipe to center of the pump to the surface level at the delivery tank. Then we have the static head, which is the sum of suction head and the delivery head. Static head is the theoretical head which we need to achieve when we are storing water in an overhead tank. But there will be losses, so to consider those losses we go for manometric head, which is HM. Manometric head or effective head is the total head plus it is the static head plus the losses on in the suction side as well as in the delivery side. When you consider those losses, then the total head which the pump has to deliver is manometric head. So the manometric head can be written as U2 VU2 minus losses which occurs in the impeller and the casing. So here manometric head is not considering the losses which occurs in the impeller and the casing, that will be considered later. So the manometric head will be equal to U2 VU2. So here we are not considering U1 VU1 because VU1 will be 0 or the fluid will be entering in the axial direction. Since the fluid is entering in the axial direction, VU1 will be 0. Energy transferred in the pump will be equal to U2 VU2. So U2 VU2 minus losses will give us the manometric head. So this manometric head is not considering the losses that occurs near the impeller and casing. Some amount of water slips through the casing and it will never reach the delivery side of the pipe or delivery pipe. So those losses will not be considered in the manometric head. We will consider those losses in the later class. Now HM is U2 VU2 minus losses, and U2 VU2 can be written as Euler's head HE. So HE minus losses that occurs in the impeller and the casing. Or HM can also be written as, with the help of this diagram, it can be written as HS plus HD, HS plus HD plus HF, this is the total frictional losses, plus Vd square by 2. Vd square by 2 is the loss which occurs because of the velocity at the delivery pipe. So that is the velocity or the kinetic energy we are not utilizing. So if you are able to bring the velocity in the delivery pipe to a very minimum value, then the losses, the exit losses will be very less. So these two together we call it as static head, that is HS plus HD. So I will write it as H capital S, which stands for the static head, plus HFS. HFS is the frictional losses that occurs in the suction pipe, plus HFD, that is the frictional losses that occurs in the delivery pipe, plus Vd square by 2. So that is the kinetic energy loss which occurs at the outlet of the pump. So that is the manometric head. Manometric head is the theoretical head that a pump has to develop when it is delivering a liquid from sump level to the delivery tank with a static head HS. So if the static head is HS, then the pump has to work extra hard to achieve the manometric head so that we can have this head difference in the delivery of the liquid. So here for the low head, medium head or high head, whatever the head we were talking, that is the static head. That is the actual head which has to be developed, but the pump has to work extra hard to achieve monometric head, and in the monometric head we are not considering the losses that occurs in the impeller and the casing. So the pump has to work extra hard to overcome those losses and achieve a static head, capital Hs. Now let us look at the pump losses. So the pump losses are divided or classified into three categories. One is the hydraulic loss, the second one is the mechanical loss, and the third one is the leakage loss. In hydraulic losses, we have the shocks and eddy losses that occurs when the fluid is flowing through different cross section of the pump, and then at the entry as well as at the exit, the cross sectional area will be changing, and because of that the shocks as well as eddy currents will be created, and that leads to loss of some fluid energy. Then we have frictional losses in the impeller, guide vane and the casing. As the fluid passes through all these things, that is the impeller, guide vanes and the casing, there will be fluid friction, and because of that there will be loss of certain amount of energy, which also comes under the hydraulic losses. Then we have the friction and minor losses in the suction pipe and delivery pipe. So in the suction pipe as well as delivery pipe, there will be change in flow area, and the fluid surface and the fluid when flows very close to the surface, there will be friction between the fluid and the stationary surface, that is the pipe surface, and because of that we will have certain amount of losses. So these are all the losses which are categorized under hydraulic losses. Then we have the mechanical loss. So in case of mechanical loss, we have the disc friction and the mechanical friction. So in the disc friction between the fluid and the rotor. So when the fluid flows between the stationary casing and the impeller, there will be a friction caused, and that we call it as disc friction. And then there will be mechanical frictions on the mechanical bearings. So we have a relatively moving element here. So one, we have a stationary casing and we have an impeller. The impeller is rotated with the help of a shaft. So the shaft is rotating relative to a bearing, and there will be always mechanical friction in that case. So those are classified under mechanical losses. Then we have the leakage losses. So here the water which enters the pump or which enters the casing, all of that will which is drawn from the suction pipe, all of the water will not flow into the delivery pipe, because this is not a positive displacement pump, this is a turbo machine, so there is no positive containment here. So some of the water leaks and goes back into the suction pipe, or that leaks and stays in the casing, it will not move into the delivery pipe. So that water would have absorbed certain amount of energy from the impeller, but since it is not moving to the delivery pipe, so that will be a loss. So those kind of losses we call them as leakage losses. So here the water which slips from the delivery pipe, so that water will have certain amount of energy, and that energy, whatever energy we are losing because of the slippage of water from the delivery pipe and the casing, so we call that as leakage losses. So these are the different losses which we encounter in a centrifugal pump. Now let us see the different efficiencies of a centrifugal pump. The first one is the monometric efficiency, eta m. So we all know that monometric head includes the head developed by the pump, the actual head developed by the pump, plus the losses which occurs in the suction side as well as delivery side of the pump. So here the monometric head is defined as the power developed by the pump divided by the power imparted by the impeller. So the power developed is nothing but the head developed. So the power and head can be used interchangeably in this case. So head developed by the impeller divided by, head developed by the pump divided by head developed or head imparted by the impeller. So that ratio we call it as monometric head. So it can be written as Hm, which is monometric head, divided by He, which is Euler's head. That is the theoretical head which can be developed by a pump, and the actual head, the monometric head developed by the pump. So this can also be written as G into mH. G into mH is the monometric energy imported into the fluid divided by U2 VU2. We should remember that in a centrifugal pump, V1 will always be in the axial or radial direction. So since it is in the axial or radial direction, alpha 1 will be 90 degree, and because of that VU1 will be 0. So in the case of pumps or centrifugal pumps, the energy transfer will be equal to U2 VU2. So here Euler's head can be written as U2 VU2, and this also can be written as HM, that is monometric head, divided by HE can be written as monometric head plus losses, or in other terms I can write HM as Euler's head minus losses divided by Euler's head. This is the different forms of representation of monometric head, which is also known as hydraulic efficiency, which is eta H. So monometric efficiency is also known as hydraulic efficiency for a centrifugal pump, which can be written as eta H. So eta H or monometric efficiency, hydraulic efficiency or monometric efficiency is the ratio of power developed by the pump to the power imported by the impeller, which is also equal to water power output, that is the actual head developed, divided by the power gain to the impeller. So these are the different equations for the monometric head or monometric efficiency or hydraulic efficiency in the case of a centrifugal pump. Then we have mechanical efficiency. Since we have relatively moving components in this pump, so always there will be mechanical losses, and because of that we need to define the mechanical efficiency, which is the ratio of power delivered by the impeller to the shaft input power, or input power given to the shaft. So that can be written as U2 VU2, that is the power developed by the impeller, that is this. Here we had used that in the denominator, that is U into VU2, or the Euler's head, divided by power developed plus mechanical losses. That will be the input power given to the shaft. Then we have volumetric efficiency eta vol. So that is the ratio of the actual amount of water delivered or amount of fluid delivered to the amount of fluid drawn or sucked by the pump. So here while talking about the leakage losses, we said some of the water or the liquid gets slipped through the delivery pipe and it will not enter the overhead tank. In that case, there will be certain amount of fluid losses, and that will be accounted in volumetric efficiency. So volumetric efficiency is defined as the quantity of fluid discharge or the liquid discharge divided by the quantity of fluid sucked by the pump, and that can be written as QD, which is the amount of the discharge at the delivery side, divided by QD plus QL, where QL is the losses leakage losses. Then we have the overall efficiency, which is the ratio of all the three efficiencies, that is the monometric efficiency or hydraulic efficiency, and mechanical efficiency, and volumetric efficiency. So the overall efficiency can be written as it can be defined as the power developed by the pump to that of the power supplied to the input shaft. So that can be written as GH divided by U2 VU2 multiplied by U2 VU2 divided by input power to the shaft multiplied by QD by QS, which is the volumetric efficiency. So overall efficiency can be calculated by multiplying all the three efficiencies, that is hydraulic efficiency multiplied by mechanical efficiency multiplied by volumetric efficiency. This gives us the overall efficiency for a centrifugal pump. Now let us look at the work done by the centrifugal pump. Before going to the work done, let us understand the velocity triangle at the inlet and outlet of a centrifugal pump. So here we have a vane of a centrifugal pump. This is just for representation. This is not the actual shape of the vane which we use in our centrifugal pumps. For centrifugal pumps, the vanes will be radial. So this is not the actual representation. Here at the inlet, V1 will be radial in direction, and because of that VU1 will be 0 and hence alpha 1 will be equal to 90 degree. Here we have, this is U1 and this is VR1. So the resultant of subtracting V1 and U1 is VR1, that is the relative velocity at the inlet. Then the fluid passes through the impeller and gains energy and gains power or energy, and then comes out of the impeller with absolute velocity V2 and relative velocity VR2, and since this is a radial flow turbo machine, so the inlet and outlet tangential speeds of the rotor will be different because the fluid will be entering at a smaller radius and leaving the impeller at a larger diameter. So because of that, U2 will be greater than U1. So U1 and U2 will not be same in this case or in any radial flow machines. This is the angle alpha 2 and this is the angle beta 2. So here, since V2 is not radial, it will not be radial, and because of that we will have a certain value for VU2. And when you consider the Euler's energy equation, so to find out the work done, so the work done by the impeller per kg of steam, the work done by the impeller per kg of water or any other fluid. So the Euler's equation is per kg of the fluid, okay, that is given by E, which is also equal to change in enthalpy, which is equal to U2 VU2, because here VU1 is 0 because alpha 1 is 90 degree. So because of that, since the fluid is radial at the inlet, alpha 1 will be 90 and there is no horizontal component for the vertical line. So V1 will be a vertical line, so there is no horizontal component for that. Because of that, VU1 will be 0. Since VU1 is 0, so the Euler's equation reduces to U2 VU2. It is minus U2 VU2, and we are not showing the minus here because this is a power absorbing turbo machine. So we are not bothered with whether it's plus or minus, since it is, we know that it's a power absorbing turbo machine. So the energy will be lost by the machine and it will be a negative in the Euler's equation. But here we are only concentrating on the quantity of energy transfer, not the direction, because we already know that it is a pump and pump is a power absorbing turbo machine. So from the outlet velocity triangle, so from this outlet velocity triangle, I can write U2. So I need VU2. So VU2 is from here till here. So VU2 can be written as U2, the entire base of the triangle, minus this section. So this section, I have written that in terms of cot beta 2. So now let us see what is cot beta 2 here. Cot of any angle or cot theta is equal to adjacent by opposite. So here this horizontal side is the adjacent side and VF2 is the opposite side for this triangle. Okay. Now I need the adjacent side. So adjacent side will be equal to opposite side multiplied by cot of that angle. So here I need this length. So this length will be equal to VF2, which is the opposite side, multiplied by cot beta 2. So that is VF2 cot beta 2. Now I will substitute VU2 in the energy equation. So energy, or G into HE, HE represents the Euler's head. So that will be equal to U2 multiplied by VU2, which is U2 minus VF2 cot beta 2. So that is what I have written here. Then energy will be equal to GH. So instead of calling Euler's head, I will just call it as head. So G into H, since we are dealing with liquids here, I am using H, because for liquids we generally use the pressure head as a reference. So I am using GH, which is equal to U square. I am just multiplying this U2 within the bracket. So U2 square minus U2 VF2 cot beta 2. And I need head. So I need to find out the relation between head. So this is the energy equation. This is the work done equation. If you multiply mass flow rate to this, you will get the power output or the power required by the pump. So now I need to know the relation between the head developed by the centrifugal pump and the discharge. So for that, what I will do is I will use the same equation. I will take G to the other side and I will write H will be equal to U2 square divided by G minus U2 Vf2 cot beta 2 divided by G. So here I need to bring the discharge term. So what I will do is, I know that Vf2 is the flow velocity at the outlet, and flow velocity from the continuity equation we know that Q will be equal to velocity into area or cross sectional area of flow. So I am using that concept here. At the outlet, Q will be equal to Vf2 multiplied by area at the outlet, and area at the outlet is given by pi into d2 into b2, where d2 is the diameter at the outlet and b2 is the width of the blade at the outlet. So width of the blade multiplied by the diameter will multiplied by pi will give us the flow area available at the outlet of the impeller. So if you see an actual impeller at the outlet, the area will be in a cylindrical area. So the surface area of the cylinder needs to be calculated to get the area at the outlet, and that is given by pi d2 into b2. So I can write Vf2 as Q, that is discharge, divided by the flow area, that is pi d2 into b2. Now when studying the variation of head with respect to discharge, I will keep all other parameters as constant, that is I will keep U2 as a constant because we are studying it for a particular impeller. So the diameter of the impeller will be fixed, U2 will be constant and beta 2 will also be fixed. So G is a constant, and D2 again, since we are studying it for a particular impeller, D2, B2 and beta 2 all will be fixed. So I will group them and call them as K1 minus K2 into Q, where K1 is U square by G and K2 is U2 cot beta 2 divided by G into pi D2 B2. So I will get an equation which is H is equal to K1 minus K2 into Q. Now let us plot the variation of Q with respect to H for different values of beta 2. So if you take a different shape of the impeller, then what happens to the discharge? So here on the y axis I have the head developed and on the x axis I have the discharge, and here I have drawn lines or curve for three different cases. One when beta 2 is greater than 90 degree, and the other one is when beta 2 is equal to 90 degree, and the last one is when beta 2 is less than 90 degree. So here we can see that all these three lines comes and meets the y axis at the shut off head. Shut off head is the head which is if the head developed by the impeller is less than that, then the discharge will be 0. That is the meaning of shut off head. So below that head the discharge will be 0. So from there if beta 2 is greater than 90 degree, then in this equation, cot beta 2 will be negative value, and because of that H keeps on increases with the increase in the value of Q or increase in the value of discharge. So for vanes which have beta 2 greater than 90 degree, as the discharge increases, since cot beta 2 more than when beta 2 is more than 90 degree will be a negative value. So this entire thing minus into negative will minus into minus will give us plus. So with the increase in discharge, the head keeps on increases and the head keeps on rises. If beta 2 is if beta 2 is 90 degree, then cot beta 2 will be 0, and because of that whatever may be the variation of Q, the head remains constant, and that will be equal to U2 square by G or K1. If beta 2 is less than 90 degree, then cot beta 2 in this equation will be a positive value, and this entire thing will be a positive value minus here we have minus. So as Q increases, the head keeps on reduces. So we have a falling head in this case when beta 2 is less than 90 degree. So this is the work done and the variation of head with respect to discharge for different cases of beta 2.